Welcome to Chemistry 2, Unit 5 Equilibrium, Lesson 1, Video 3. So in this video, we're going to look at equilibrium as a dynamic state. And what this means, dynamic state, is that it appears as though the reaction stopped. So nothing really looks like it's changing, but both the forward and reverse reactions are happening. So even though it looks like the concentration of products and reactants is done, it's stopped, it's static, they are constantly being reacted, produced, and then reversed. So they are being formed and then broken down again. But since the rates have equalized, we end up with this dynamic state in which it looks like the reaction has stopped, but there's still a lot happening. And we're going to use this example. This is a pretty famous equation. Nitrogen plus hydrogen yields ammonia. This reaction normally doesn't take place. So if I put nitrogen and hydrogen together, I don't have ammonia forming. This reaction has a catalyst that drives this forward. And it took a lot of time and conditions in order to figure out how to get this to happen. Because ammonia is a starting block for a lot of things that we use in society, and it has really changed how things work in the world. We used to have, with crops, especially agriculture. So this ammonia is a starting block for a lot of commercial fertilizers, but it's also the start for rocket fuel. So the person that came this up, his name was Fritz Haber. He actually won a Nobel Prize for it. He was German, and this happened in the early 1900s or so. And this ushered in a lot of the bombs that were made in Germany. So it was kind of a good thing and a bad thing. It helped agriculture tremendously, but it also increased bomb production because ammonia is the starting block for a lot of rocket fuel. So with this, and the catalyst that he used, I believe it's like at 500 degrees Celsius. It's under high pressure, but it's a platinum iridium alloy that they put this on the surface of, and it allows this to happen readily. Before, you would have to plant certain plants like soybeans that would take nitrogen out of the air and fix it into the soil to get it to fertilize. And that's still done today if it's an organic field. So it's a natural way to put nitrogen back into the soil that the plants take out. So if we were to look at this equation and we were to graph this equation, we're going to start down here at 0, 0, the origin. And we're going to have time on the x-axis, and we're going to have concentration of the product, reactants and products over here. So we know that if we start with a certain amount of each one of these, our concentration is going to be maybe here and here. So over time, the concentration of the reactants is going to decrease until it levels out. So it would look like that. This one would look very similar. So this could be N2 and this could be H2. So they start out high and then they decrease rather rapidly, and then it starts to slow down and then it becomes even. NH3 over time, well, it's going to start here at 0 because we didn't have any, and it's going to increase, and eventually it is going to level out also. The point where they all are basically constant because this is being broken down at the same rate in which these are being formed. This is our equilibrium point, and the time it takes for that to reach can be calculated. But what we're going to be concerned about is what are the concentrations when this point is reached? what could we do to increase this value and move it upwards? So we're going to start talking about how we use the numbers in order to figure out concentrations at equilibrium or figure out the equilibrium constant so we can predict things.